Welcome back to the CS4423 networks. My name is Götz and this video is about bipartite graphs. We want to look at this type of graphs from a theoretical perspective and also from a practical perspective, how they can be used and handled from within the networks package. So we load the networks and NumPy as well, as it might be handy later on. Also, we fix some options for the drawing of graphs, as we've done before, to have the labels drawn and the nodes colored in yellow. Now, a simple graph G on a vertex set X with edge set E is called bipartite if the vertex set X can be partitioned into two sets, a set B of black nodes and a set W of white nodes, in such a way that the edge set E connects black and white nodes only. Each edge in the E set is a connection between a black node and a white node. There is no edge between white nodes only, no edge between black nodes only. Here's an example of a bipartite graph. Let's call it B. It's specified by a list of edges, which is passed to the graph constructor of the networks package. 11 edges on 10 points. So if we draw this, it might not be immediately obvious that this is a bipartite graph. But we can try and split the edge set into two halves. Okay, so here upon further inspection, if we take for the white nodes the first 5, the nodes from 0 up to 4, and for the black nodes the nodes from 5 up to 9, then this turns out to be a partition of the vertex set, so that all the edges only go between black and white. To illustrate this visually, we pass through the drawing command an optional argument, an additional argument in the form of a dictionary pos that specifies for each node in the graph a position in the drawing. So this dictionary takes the nodes as key, and the position is a pair of xy coordinates. And to produce such a list of xy coordinates and turn it into a dictionary quickly, here I'm going to use Python's remainder and quotient and remainder operator, the diffmod operator, which takes a number and which takes two numbers and computes at the same time the integer quotient and the remainder. So for example, divmod 7,5 is 1,7, representing the fact that 7 is one multiple of 5, remainder 2. So in order to separate the nodes from below 5 from those above 5 and put the first set on the left of the drawing and the second set on the right of the drawing, I compute the quotients and the remainders. I take the remainders as the y positions and the quotient as the x position, and turn this into a dictionary like this. And then we see that I'll compute the remainder modulo 5. We see that node number 7, as before, now gets coordinates 1, 2. 1 as an x coordinate, 2 as a y coordinate. So it ends up on the right side of the drawing at level 2. And similar for the other nodes. And passing this positions dictionary as an additional option into the drawing command. Now draws the vertices from 0 to 4 on the left and from 5 to 9 on the right through this calculation of and assignment of positions. And drawing the graph in this way, we now see that all the edges go from the left to the right, or from the set of white nodes to the set of black nodes. There's no edge between the black ones, no edge between the white ones. This way of drawing the graph shows in a visual way that this is actually a bipartite graph. To emphasize this even further, we could color the nodes in black and white. We could actually put a color coding on the two sets. Now, this again can be done as follows. And we can pass to the drawing command node color argument, which assigns not so much a color but a number to the vertex, and then the drawing command chooses colors matching the numbers in some way. So here, since we've separated the two nodes according to their x coordinate, we can use the x coordinates now at the same time to encode the different colors and compute a list of colors as the x coordinates of the nodes. So we get this list of colors. This might look a bit surprising because shouldn't the first 5 nodes have color say 0 because their x coordinate is 0, and the remaining 5 nodes then have color coordinate 1. This list here is not zeros followed by ones. Well, the reason for that is that subtly, node names need to be distinguished from the actual index of the node in the list of all nodes of the graph. Here, the node names, the set of node names is the same as the set of the indices, so this can lead to confusion. But to show you what I mean is, if we print the list of nodes of the B graph, then the order in which they are stored in the graph is actually 0, 5, 1, 6, 7, 8, 2, 3, 9, 4. That's the order which resulted from, I guess, constructing the graph edge by edge. So reading through this edge list, the graph first learns of node 0, and then it learns of a node named 5. So this is the first 2 nodes that are installed in the graph. 0 comes at position 0, but 5 then is the next node, and that's stored as at position 1. So it's in this order that the nodes are stored, and according to this order we need to encode the colors. So once that is done, we can pass this color code to the drawing command. Here I've constructed a new options dictionary called opt2, which has the node color argument and an additional font color argument to draw the labels in red, so that we have a chance of reading them. With that in place, then the nodes on the left are dark purple, the nodes on the right are yellow. And with this color coding attached to the graph, maybe we don't even need to separate the nodes to the left and to the right. We can just draw the graph, and then with the colors attached to the nodes, we see that each edge goes between a yellow and a purple node. Now, such a coloring is called a vertex coloring in general. And you might have seen this, you might remember this from the graph theory in second year. A vertex coloring of a graph is an assignment of colors to the nodes of the graph in such a way that an edge always connects nodes of different colors. Then with that notion of coloring, a graph is called n-colorable if it has a vertex coloring that uses at most n colors. So in that sense, each graph presents a competition who can color the graph with the least possible number of colors. Now, in the present context of bipartite graph, the following are equivalent descriptions of graphs that are bipartite. Number one, G is bipartite. Number two, G has a 2 coloring. G is 2 colorable, as we saw before. And a third equivalency is that each cycle in the graph has even length. For the specific definition of cycle and length, we'll come to that later next week. There's a family of graphs, 2D graphs, 2D grid graphs, which are naturally bipartite. We can ask the networks package for such a grid graph, or a 4x4 grid, for example, on 16 nodes. And this gives some sort of chessboard pattern, if you like. And sure, on a chessboard you can color the squares alternatingly black and white. And that's exactly the notion of two coloring that we have in mind here. The package has a function, has an algorithm, bipartite.color, which determines a two coloring of the graph algorithmically if it exists, that is, if the graph is actually bipartite. If we apply this to the 4x4 grid, now then we can we can compute a coloring in this way. This we don't need. And so this is this assigns to each node a color. You see that the node names here are pairs of numbers. This is a grid graph. So you can read this as each node has an x and a y coordinate, if you like. And these x-y coordinate pairs here serve as node names, and to each node name there's a color associated. We saw in the earlier example that in order to pass this color information as an argument, as a parameter into the drawing command, we need to match the colors. We need to list these colors in the exact order in which the nodes appear in the graph. So we can do this through such a list constructor. List the colors in the order of x as x runs through the nodes of the graph. That gives us a list of colors which we then can enter into our opt2 dictionary of drawing options, and then when we draw the graph we get a colored drawing of the 4x4 grid with colors alternating as on a chessboard. Okay, now let's apply this to a useful example of networks. In the context of networks, in the context of social networks, one frequently deals with so-called affiliation networks. These networks, by their very nature, are bipartite graphs. In such an affiliation network, you have two types of nodes to begin with. One node type, let's say the black nodes, are people, and the white nodes are certain attributes that these people share or not, like workplaces or interests, as in books they bought online or TV shows they're following or social events that they attended. And the edges in such a network connect people with these attributes. Connect each person in the network with all the books they ordered online or all the shows they watched. And so by construction, this affiliation network lives on a set of vertices that consists of two different kinds, and the edges go between those two kinds, between people and their workplaces. A frequently cited example from the literature, sociology literature, is the so-called Southern Women Network. This goes back to the 1940s, and it's a collection of data concerning 18 women which have been observed over a 9-month period attending sequence of 14 social events. And this table records the attendance of the women at the events with the dates, and if that table with its noughts and crosses reminds you of a adjacency matrix of a graph, then you're on the right track. Anyway, we can use this information to define a graph on a vertex set that consists of the union of the list of women here and the list of events. And whenever a woman attends an event, each cross here in this list then represents an edge between the woman and the event. And this graph is actually contained as an example graph in the networks package, and we can call for it as the Davis Southern Women graph, which has the following list of nodes. There's a list of names followed by a list of events which are just numbered E1 up to E14. And if we draw this graph in the usual way, then we get quite a big graph, which is a challenge to read, but you can, by inspection, you can verify that the edges connect proper names to these codes for the events. But it's certainly not the nicest presentation of this graph. But as before, we can ask for a coloring of this graph, which gives us a list of colors. This time the ones are followed by zeros. And if we add this color information to our options dictionary, then we can draw the graph in a colored way. And that's already nicer. Here it's already easier to see that edges go between people and events. Now, upon closer inspection, it becomes clear that the adjacency matrix of such a graph, the adjacency matrix of a bipartite graph, where the nodes are sorted as they are here, so that that ones are followed by zeros, that all the nodes of one kind come first, and then come the nodes from the other kind. With respect to such an ordering of the vertices, the adjacency matrix has the form of a 2 by 2 block matrix, as it is here, where, say, you have the black nodes first, the people first, and then the white nodes, the events in this case. The fact that there are no edges between the B set at all makes for a square matrix of zeros, as many rows and columns as you have elements in the B set, representing the fact that there are no edges between B's, between people at all. Same for the zero down here, which might be a zero matrix of a different size. It has as many rows and columns as there are in the W set. There are no edges between elements of the W set, so all these entries here are zero, and all these entries are zero, which make for lots of zeros in this 2 by 2 block form of the matrix. Now, off the diagonal, then you have the edges, and sitting in a smaller matrix, which I called C here. And these are edges going from people to events, and corresponding to that, you have in the bottom left entries 1 in the adjacency matrix for edges going from events to people, which are the same edges. This A matrix, the adjacency matrix of a simple graph, is symmetric, so it is its own transpose, and that makes the matrix in the bottom left here the transpose of the matrix up there. The transpose matrix exchanging rows and columns. And that's the general structure of the adjacency matrix of a bipartite graph, with respect to the vertex set being ordered in such a way that the black vertices come first, followed by the white vertices. Let's see, is this the case in our example? Well, if we just print the adjacency matrix, Python decides to print this in such a small fashion that we don't really see a thing. So we need to set some numpy print options here in order to get the full matrix. But there it is. And what one can see is lots of the zeros in the upper left corner, and lots of zeros in the bottom right, and you see a matrix of zeros and ones in the upper right. And if you look at this for long enough with some visual yoga, you can see that the matrix of zeros and ones at the bottom left here is the transpose of the top right. So this means that the incidence information, the connectivity information of this network, of this bipartite graph, is really contained in the C matrix up here, in this rectangular matrix of zeros and ones. You don't need the full adjacency matrix for that information. So how do we access this in the networks? Well, this works as follows. In networks, and we'll see more of this as we go on, all the elements of a graph can have additional attributes. We can store attributes with nodes, we can store attributes with edges, and we'll see how this can be useful as we keep working with these graphs. Here we have attributes stored to the entire graph. And there's a the graph has a component called graph, which is a dictionary that stores attributes that refer to the entire graph. And here, in the case of a bipartite graph, there are attributes called top and bottom, which contain the black and white sets of the subsets of the bipartite graph. So if we call these sets x and y for the moment, the one set the graph top and the other set the graph bottom, then we can ask networks for the bi-adjacency matrix of the graph G with respect to those sets x and y, and C will then be this rectangular part of the adjacency matrix on the upper right corner from the big adjacency matrix. Now, the adjacency matrix itself, I've said this is symmetric, so it is its own transpose. So it's the product of the transpose with A itself, or the product of A with itself, they're all the same, and they can be computed as by matrix multiplication, and they then come out as a matrix, again as a block matrix, which now has zeros in the off-diagonal positions, big matrices of zeros, and on the diagonal we find the product of C and its transpose, and down here the product the other way around, C transpose times C. Turns out that these products are adjacency matrices of graphs. They are the adjacency matrix of the projection onto the black vertex set, or the other one is the adjacency matrix of the projection on the white vertex set. So we can use this information to construct new graphs. Now this is we call it BB, the projection on the projection onto the black vertices obtained from multiplying C with its transpose and then reading this as an array and feeding it back into a graph constructor. Now this gives a graph which looks like this on 17, 18 vertices. Okay, we actually want this to be the graph labeled by the women, so we need to relabel the nodes in this graph with the names of the women concerned, using the relabel nodes facility that we saw yesterday, and then we get a graph between black nodes only, between people only, where if you think about it, two women are connected if they ever attended the same event. That's what this product C times transpose of C expresses. It's an edge from a woman to an event, followed by an edge from that same event to possibly another woman, and that gives an edge from that woman to the other woman, indicating the fact that they attended the same event. That's the projection graph on the set of women only. And okay, the networks package has its own function for that, and the projected graph function computes exactly that, the projection on the set of top nodes, as it's called in here. In a similar way, we can compute the projection on the events only. This gives a graph on the event set, connecting two events if they were attended by the same woman. Two events are connected if there is a woman that attended both. That results in this graph, and this might have some meaning. This is these attending say the same event establishes a relationship between the people involved, and the graph structure might tell us something about the relationships between the people, their degree of how much do they have in common, their importance maybe. We'll turn to such questions and how they can be answered from the graph soon. For now, I want to finish with looking at the actual matrix that is C times its transpose. And we see that this is not. It's a square matrix to begin with, but it's not. It doesn't look like the adjacency matrix of a graph, since the entries are not just zeros and ones. But that's something we saw in the previous lecture, how to fix, how to turn values bigger than 1 into ones, how to turn the diagonal values into zeros. And in fact, in order to use this matrix as a description of a graph, of a simple graph in the networks package, we don't actually need to do this. So we can pass this matrix as it is, and the networks package that's what we did here, it will construct a simple graph from the information that's there and interpret it in the right way. As usual, there's a few references and some exercises at the bottom of the notebook. That's it for now.